In this video, we're going to take a look here at example number 3. We're going to look at 3 different vector functions, and we're going to try to go ahead and see if we can understand a little bit about how we could attempt to sketch these different vector functions. Now, what you'll notice interestingly about the first 2 vector functions is that they are vector functions that actually only have 2 components. You'll note here that if I was to rewrite these vector functions, so they're not in the I, J, K form, but just in the kind of angled bracket form, I would have vectors that look like this. So that's my first vector function. And down here, I would have this vector. Okay. You'll also notice that with these vector functions, I'm including a restriction on t, right? So there's only certain values of t that I'm going to use. So we're going to go ahead and try to sketch a quick graph of what each of these individual vector functions might look like. So really quickly here, I'm going to go ahead and start to think through this first one. Now, I have to keep in mind that when I'm looking at the vector here, I have to remember that my first component here represents x's, and my second component represents y's. And actually, if I do that here, I kind of can see a really interesting connection automatically between the x and the y that I have. I'll even write this off at the side. Okay, so here, note that t squared minus 2t plus 1 is actually related to the quantity of t minus 1. In fact, it's related because if you were to square a t minus 1, you actually end up getting what we have for x. Now, this doesn't necessarily occur with every vector function, but it's an interesting thing to note here, and it actually lets me understand what this function looks like much more easily. Because I'll notice then this really implies that x is equal to y squared. Notice I just kind of replaced my first part here with x because that's what it was representing, and my t minus 1 with y because that's what it was representing. And if I wanted to know what this graph looked like, well, that's super easy. That's a sideways facing parabola. Now, I have to be aware that I'm only interested in sketching this sideways facing parabola, which I'll loosely sketch out here. I'm only interested in graphing it on the interval where t goes from 0 to 3. So what I'm going to do is think about, like what x value am I at, say, when I plug in 0, and where am I at other values? Well, let's see. If t was a 0, you can notice right away that I should be at the x value of 1. And of course, my y value at that point would be negative 1. So that means that there should be a vector pointing out from the origin to the point 1, comma, negative 1. And let's suppose that that's right here, 1, comma, negative 1. I don't need to draw the vector that's kind of shooting out that point like we talked about in the last video, but I will note here that this occurs when t is 0. Now, if I was to say increase t to the value of 1, I'll notice that my y value is going to go to 0, but also I should note here that since x and y are related, because x is really just t minus 1 squared, well, my x value should also be 0 if t is a 1. So that would mean that I'm actually going to be over here when t is equal to 1. Just adjust that. Okay. So what's kind of cool is I can kind of imagine then the path of the particle, or a particle, on this particular curve. I could imagine even filling it in. Like my particle, if it was moving along this path, would have to kind of move in this direction. So I can include some sort of like arrow indicator on here to show how the curve is increasing, okay? Or the direction the curve is oriented. Now, if I was to plug in the value of 2, I'm actually going to end up here at the value of 1, 1. There would be a vector that points out there. And so I can see that I should keep moving. This is when t is equal to 2. And finally, if I was to go ahead and get to t is equal to 3, that would give me an x value all the way out, say, at 4, and a y value up at 2. And let's suppose that that's going to be this value right here. Okay, you can double check that those are indeed the correct coordinates for that point. And so this would be it. This is the entirety of that curve. It actually doesn't extend into any more of the black dashed area. It's just this blue portion. So sometimes we can be aware of these little connections between x's and y's that can help us understand what a curve looks like. All right, let's look here at part B. In part B, we're going to actually recognize something really, really interesting because this sort of a vector function, or these components of this vector function, are really important ones. They're going to pop up a lot this semester, and we really want to make sure we understand what a graph is going to look like when it has this kind of cosine component and a sine component. Okay. If we go ahead and take a look, we could start by thinking about plotting some different points. Could start by plotting some different points using the restricted values of t that we have. So let's just use some simple values. Let's suppose we start with t at 0. If I was to do that, I could say, what is 4 times the cosine of 0? Okay, well, cosine of 0 is 1, so that should get me the value of 4 in the x direction. And the sine of 0 is just 0. So when t is 0 here, I'm actually exactly at this point. This is when t is 0. Okay, there would be a vector pointing out from the origin that plots that point, moving right along the x-axis. All right, well, what if I moved up to a value of, say, pi over 2? I know the cosine of pi over 2 is 0, and I know that the sine of pi over 2 is 1. So that should get me the value of 2 up here. That would mean I have a vector that is going to point right up to this point. And if I have to move from one to the other, it's actually going to be in a somewhat kind of smooth oval-like shape. Again, I arrive up here when t was pi over 2. If I progress to t being at pi, then I'm just going to end up with a value of negative 4 in the x direction, 0 in the y direction. I'm over here when, again, t is pi. And if I was to go up to t is a 3 pi over 2, if that's what I had for t, then I would get down to a value here of negative 2. If I was to go all the way to t being 2 pi, I would actually find that I'd be right back to where I started. Okay, so when t is equal to 2 pi, actually I'm at the same exact spot that I was when t was a 0. So this is interesting. What I've created here is ultimately some sort of oval-like shape. And the interesting part here is you might remember that the cosine is typically associated with like an x direction on the curve. And here we see that this 4 in the front is representing how far out I've moved in that x direction. Similarly, the 2 is representing how far I've moved out in the y direction at the extremes. So an interesting thing to see here is like, what would have happened, or what would the shape have been if this, instead of being a 2, was also a 4? Well, I could imagine that this point here and this point here would have been stretched up and stretched down, and I would have gotten the picture of a circle. So I would encourage you to go ahead and make a quick note for yourself here that when cosine of t and sine of t are in our components, or in our component functions, we have an ellipse. Now, an ellipse of some sort. Now, again, remember, it could be a circle, but that would just require that the numbers in front here are ultimately going to match. But this is going to be really crucial. You'll see this happening all the time where we'll kind of say, hey, look, if you look in the components here, you'll see a cosine over there and a sine over there. What shape is that? And we're going to have to say, oh, that's like an oval. It's an ellipse, or maybe it's a circle. That's really, really valuable for us. Okay. We'll actually see that here if we take a look at part C. Notice right off the bat, here I'm in the world of 3D. I have 3 components here. If I rewrote this in vector notation, I would have 2 cosine of t, I would have 2t, and then I would have sine of t. So this picture is going to be in 3D, but I'll notice again that if I was to only say look at the x direction and the z direction, what sort of shapes should I see? And again, we could say, oh, I see circles, right? Or I see ovals, right? Something like that. In here, it looks like it would be an oval, probably stretched more in the x direction than it is in the y, or sorry, in the z direction. So let's try to get a sense of what this might look like here. I'm going to go ahead and try to draw out a graph with my x, y, and z axis. I'm actually going to angle my y axis here a little bit more out so I can draw on the other side of it. I'm going to include some negative axes here as well. Okay. But notice I don't really need a negative y-axis because my value of t here can only ever be at small, well, it's only at smallest 0, and my y's are always 2 times t. So what's interesting here is that you'll notice that when you look at the different components that I have, there's actually only a limited number of values that the first component can ever take on, right? Because cosine is like it's a restricted function. It's only ever going to spit out values from -1 to 1. And so this component can only spit out values from -2 to 2. Similarly, this z component can only spit out values from -1 to 1. However, this y component can actually spit out values from 0 to, I guess, as large as I want. All right, let's try to get a sense then of what's going to happen here in our picture. I'll start with, say, the first point. If t is a 0, notice that I'm going to actually be out here at 2 on the x-axis. I'll be at 0 on the z-axis. And I'll also be at 0 on the y-axis. So I'm going to get a vector that points right to this point, and that's it. But notice that something interesting happens, say, if I go to, let's say, pi over 2. Right? If I went to the value of pi over 2, then notice on my y-axis, I would have to be at pi. My z-axis, I would have to be up at 1. And on my x-axis, I would be back at 0. So I would have to have a point that's kind of like up here in space. It's 0 down the x, pi down the y, 1 up. And these guys have to connect. What's happening here, again, this happened at t equals 0 and t equals pi over 2. But what's happening here is I'm creating kind of the start of this oval type shape. You could imagine that if I went to pi, then I would have a curve that kind of comes down as well. And it's not going to be as high in the z direction. The z is going to bottom back out to 0. And then I'm going to get something that's going to kind of like loop around. The issue is that I can't really loop back to where I started, because every time I plot more points here, the t is increasing, and that means that my y value is increasing. So I kind of have to say that by the time that this comes down and hits the xy plane, I'm actually way further out from the origin than I was before. And then eventually this is going to have to go like underneath the xy plane, and it's going to like dip below that y-axis until finally it reemerges, maybe say over here. And then it's going to have to go up again and keep drawing that same circular pattern until it hits the y-axis, or the xy plane. And then it's going to dip below again. And then it's going to hit again. And it's just going to keep going. So I get this kind of, I guess you could call it like a spiral shape. Isn't that kind of weird? You can almost kind of make sense of it, though, from the formula. And this is why it's so crucial to understand how the cosine and sine are impacting what's going on here. The cosine and the sine are forcing this kind of circular shape, or this oval shape, in the xy plane. Like you could imagine that if you smushed back the slinky short shape here into the xy or the xz plane, that you would have this same sort of like ovally shape. But because of this middle part, that slinky shape is getting stretched, and so you're seeing the curve kind of progress out into space. Now, if I went to the 3D plotter, I could actually try to plot it in here as well to get a sense of what this looks like. And let's see here, maybe I want to go ahead and do a much larger value. It's a little bit hard to see here. I might have to adjust some of my uh, um, axes. You can kind of see I'm starting to get that curve, but it's just happening really slowly. If you ever want to adjust how far the X and the Y axes will show, you got to click on one of these first two buttons up here. I always forget which one. It's not the second one, it's the first one. And in here you could go ahead and make some adjustments. So like you could see like what happens if I stretch Y out to be say 20, right? Now I can start to see, oh yeah, there's that kind of slinky spiraling shape that we were attempting to draw, that it keeps spiraling around and looping through. Very similar to what we had. So understanding graphs again, and these kind of different pieces of what I can understand, whether it's connections between the X and the Y, basic sorts of shapes, or the idea that a variable is kind of unbounded and can stretch a graph in a particular direction, are all really important things to be aware of. And we'll talk a little bit more about how we can kind of go in the reverse direction and see how we can take a function's graph and try to identify its formula in the next video.